Hello, my name is Verónica López. Welcome to my talk. And I'm so happy to be part of the Go Systems Conference 2020. Just a quick introduction. I'm a software engineer currently working at DigitalOcean on the systems team and dealing with virtualization, hypervisors, QEMU, and all that type of stuff. And in my spare time, I try to help with in the Kubernetes team, and specifically on the release team. Most recently, cutting beta releases throughout different cycles, but also like helping with documentation and any like small task that is needed. I have studies in physics and computer science, and this is important to mention for the purpose of this talk, because that eventually led me to the formal study of distributed systems, but only after spending a few years in the industry working with actual distributed systems unknowingly. So I actually went to school and then I started working and then I started dealing with this type of systems and I figured out that I still needed to formalize a lot of concepts. I'm not saying that this is the only way that you can do this, but that is what ended up working for me. And so I slowly discovered that it was a passion of mine. I really enjoy working with distributed systems. So yeah, I went back and then I did a little research project, which got me a diploma on distributed systems. And I joined my mentor's research project that is basically on how to formally verify a distributed system, but without the traditional methods of the formal verification languages and all that. This is instead based on algebraic topology. You can find our work and talks on the internet, but probably the most important reason why I'm here is because working with these systems bring me like a lot of joy. So I hope that I can transmit you that. Um, okay, so before getting started, here's a quick outline of my talk. Warning, this talk will be a bit different from what we're used to in the Go community because I won't be talking about benchmarks, I won't be live coding, I won't be doing stress tests or talk about how great a library is or a package is, etc. Instead, I would talk about common pitfalls that I have seen over the past few years based on how modern distributed systems are built nowadays. And at least in my experience, I have seen that the modern distributed systems are mostly based on Go or the cloud native ecosystem. So this talk will be heavily biased around that. And also because that is my experience, right? So this talk is more about some of the things that we should be taking care of way before starting to write any lines of code. So as an introduction, I will be referring to two main concepts that to me are the very important items to keep in mind while designing distributed systems and picking the tooling to build them. Because like tooling, as we will see throughout the talk, is very, very important, to say the least. The first one is the study of the interconnections of different pieces of software, starting by defining the differences on how they operate by themselves, like in isolation, but also how do they interact with the other pieces, both partially and as a whole, like as a full system. Uh, and well, dividing and conquering helps us to design better, more resilient, but most importantly, simpler distributed systems. And so, yeah, here you can see a little figure, and you can see how I don't know how to call it, like a sphere or this geometrical shape, it is divided into little pieces. And so in our algebraic topology studies of distributed systems, we like to define each of all of these divisions as like little graphs, like nodes and vertex and all that. Uh, but like in a as a topological body. As I said, I won't be talking about this during this talk because there are other talks about it, but I'm just giving you some context for you to see what I'm talking about and what am I referring to? And also it is important that when I say topology in this type of things, I'm referring to the maths, not to the computer science or engineering term topology, where engineers use it to describe like the how a system looks like and the layers, you know. So this is more in mathematical terms. The second concept is the OSI model for distributed computing, which clearly defines the layers of our system. Although this is old or like not innovative for many, it's still very relevant and useful to remind us at which part of the stack we're working on. Being mindful about these layers will be incredibly useful for the context of this talk. So we have the application layer, we have the programming model layer, then the languages, then the topology, not the maths one, the other one. Then we have the VMs, and then we have the operating systems, and finally we have the network layer. This is very important for the context of this talk, and you'll see why. So, as I said, well, the first concept that we will talk about today is faults versus failures. So, some time ago, I heard about the difference between a fault and a failure. I have seen that in modern distributed systems, these concepts are usually like mixed or interchangeable, and I'm not saying that that is wrong, but for the sake of this talk and simplicity and other reasons, um, I really like to separate them, and you'll see why. So, for instance, let's say that a fault represents an incorrect internal state in a system, while failure represents the inability of the system to perform its intended job. If this is not 100% clear for you, I'll give you some examples. So, for instance, a fault can be, mm, for example, one, a block Go routine or a dependency failure at any layer, which has become very, very popular with Go modules and all that type of tooling, which, please don't get me wrong, I'm totally pro that type of tools, but at the end of the day, it's things that we have to deal with. How about Bazel and stuff like that? So, yeah, anything around dependency failures, like forgetting to add them, which I know that this is not that common in the Go ecosystem because like all the Go formatting tools avoid that, but it's still possible. Or sometimes it's more not in the code, but more on us as engineers, like forgetting the interconnections, like not being mindful of like when we're adding this package that it might interfere in a very wrong way with this other package and so on. Um, Another fault can be memory leaks or even corrupt data, you know, like when your code, your program doesn't fail, it compiles, but the content of the data it is working with is wrong, you know? So on the other hand, a failure would imply more serious things like losing valuable uptime, usability, or availability in our systems. You know, so it's like more like harder problems to solve. But the way both of these interconnect is like when we allow the first ones, like the faults, to propagate or cascade, we end up with actual failures. You know. And that is exactly what we're trying to avoid. But how do we do it? So we design for failure. This is not to be confused, please, with a famous entrepreneurial phrase or concept of fail faster, because unlike them, in this context, we don't want our systems to crash on purpose. I mean, unless, of course, we were building a chaos engineering tool or a similar framework to inject dependencies and stuff like that. But that's a whole different story, and we're not talking about that today. Um, it's more about just preparing in case it happens. And what are you doing? And every single aspect, like how are you handling it on your code, up to like not about the code itself, but about how your engineering culture deals with this during on-call or during like production or stuff like that. So The thing is, like, it will always happen. And maybe some engineers are still not very comfortable or are not used to thinking in terms of failure, because obviously no one wants to fail. But the beauty of distributed systems is that the larger they are or the more complex they are, the more components that they will probably have. So this means that uh, more chaos is injected into the equation. So this reminds me of a very, very popular quote in distributed systems, but I find it very relevant for almost every single talk. Um, that, like, by Leslie Lampard. He said, a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. So this sounds maybe like a pun or like a joke or something like that, but it is actually the truth. Like, anyone that has been working with distributed systems long and complex enough will know that this is 100% true. Like, whenever something fails, it's more often than not, we don't know immediately what is failing. We often have to play detective to see what is going on. So, yeah, going back to the consign of this talk is design for failure. But okay, what does that actually mean? So, designing for failure, I mean, obviously the list out there is not only what I'm about to talk about. It's not only about the content of these slides, but I'm just here to share, like, humbly, the strategies that have worked for me and my teams and places that I have collaborated at. Um, so I think it all comes down to 4+1, and you'll see why the plus one. So this is a strategy that most cloud providers use, for instance, because we cannot afford to lose uptime at our customers' expense, which is, like, different from a product company or any other type of software in which you only have, like, you fail through yourself. But in case of the cloud providers, we all have, like, we are the middle person or the middle item for um, our customers and their customers. So when they fail, when we fail, they fail, and their customers are often not interested in knowing that the failure is because of the cloud provider or not. They just are unsatisfied and are unhappy with what is going on. So we really try to not to avoid this happening, right? So since we cannot effectively babysit every component, because we would never be done, we try to plan ahead, right? So first of all is that each application component must be deployed across redundant cloud components, ideally with minimal or no common points of failure. So, like, all of this, by the way, might sound a little bit too obvious, but I get reminded time and time and again that the most obvious things are usually not the first path that we tend to follow, especially as software engineers, in which that is like a career where we sometimes try to do our best to really show everyone what we're capable of, and, like, how uh, like, to show all of our knowledge, and which can lead into designing or implementing very complex systems, which is not always a good thing, right? So, well, the second thing is partition tolerant components. This means that each component should be tolerant to or able to survive network latency among the nodes that support that component without crashing or failing or partially or totally, or keep the entire system hanging. Because, again, thinking of the end user, at least for cloud providers, uh, the UX or the usability is ruined for them whether the system crashed partially, totally, or if it's just like a go routine waiting for without a wait group or any other policy, So we have to be very mindful of that. Number three, for designing for failure is our distribution policy. This means that to ensure availability of components, we must distribute them across availability zones. Of course, take this. I'm not saying that your company has to have many different availability zones and all that. If first of all, it doesn't make sense, or second of all, if you cannot afford it, or stuff like that. But try to take this advice and adapt it to your scale, at your scale. Probably you don't have different availability zones, but you have different fleets of servers, and maybe in the same region, but that service redundancy components, stuff like that. So try to adapt it to your scenario. They'll work. So okay, the number four uh, is that you have to consider latency. So we have one, two, and three, and they all sound like okay, perfect. We're ready for success. But this would be like, I would say, like the trade-off. You can implement all of this, but in case there is a very important latency ratio or very high latency index in which your usability is not friendly enough, then in that case, we must plan for close location of resources. And as simple as that. Um, and well, the plus one is here I listed as the fifth one, but uh, it is plus one because this will really depend on your own system and your own conditions. That is, consider the worst case scenario. This will definitely depend on your type of business, your application, the size of your team, or your tools, like stuff like that. But the thing is, like, you have to prepare your system to to face that. Even if you never face it, or if you face it partially, the best thing is to prepare yourself to face it. But most importantly, your engineers. So this leads me to our second topic, that is panic and isolation in Go. If you're familiar with my work or with previous talks, you'll know that even though most of my work is in the Go ecosystem, my favorite programming language is actually Elixir. Outside of that community, people tend to think that Elixir is an Erlang framework, but it is not. It actually is a full programming language on its own, obviously based on Erlang, only with a friendlier syntax and other things that, for the sake of simplicity on this talk, doesn't matter for now, but still based on the Actor model of concurrency compared to the CSP model that Go is sort of based on. Not to pit each language against each other, that is never my purpose. But one of my favorite things about Elixir is that it has fault tolerance built in, thanks to its processes and the Actor model and all of those things. I won't go into detail because there is enough information about it on the internet, in very good blog posts and talks and so on, tutorials even. In particular, I can recommend Jose Balim's and Sasha Jurik's work, but I just wanted you to be aware that such tools actually exist. And while there will always be trade-offs, because remember, there are no silver bullets, having built-in fault tolerance makes it really easy to overlook some of, say, trade-offs, to be honest, or at least in my experience. In particular, one of the things that I dislike about Go is how easy cascading failures can happen if we're not aware of components that can trigger them. So that's why we have to manually isolate our components. And with manually, I refer to like either manually in the code or with a third-party tool. But yeah, probably what I was trying to say is that we have to do this mindfully, like to really keep in mind that this is an absolute possibility and we have to take care of it. Either with a third-party tool, as I said, or designing ad hoc strategies for it. Yeah. So, um, yeah, some time ago, I asked this question on Twitter. How do you deal with fault tolerance in Go? And the reason I'm laughing is because I got a bunch of funny but also enlightening responses. I covered people's identity because I didn't ask them for explicit permission to be directly quoted, but you can still find these tweets on the internet, so it's public. And so, as you can see, the answers went from patience and with my tears during on call to asking for a more specific question or clarification, which this was actually the most enlightening part for me because while I was using Elixir or Erlang for distributed systems for us, the this same question is easily answered as like thanks to the processes, thanks to the actor model, thanks to I don't know the built-in fault tolerance or any other type of answers like that that are very specific to like built-in tools of the language. And in Go, people say like this question is too vague or it really depends on what layer you're referring to, things like that. I'm not saying that these people were wrong. I'm saying that this really opened my eyes on how fault tolerance is perceived in the Go community, right? So, yeah, this also helped me understand how important it is to have build the building blocks that enable this, or how useful it is for a programming language or tool to offer fault tolerance mechanisms outside the box. The problem with that is that not a lot of people are aware of it. Therefore, it is easy for them to think that tooling bloating is the norm. This was my favorite response, though, not only because it was by a very dear friend, but because it is also one of the ones that really opened my eyes and one of the inspirations for this talk. Because she said, well, you have to be designing systems that fail well. Latency and fault tolerance, and all taking care of all those things. And well, she used to work for a very big company, so all of the tooling to keep that in mind were built in-house, but this means that it is possible, of course, that it is not like it depends or it is very hard or it is impossible or things like that. It's like it's totally doable, but we have to be mindful. So this doesn't mean that there are not good examples of fault tolerance policies in the Go community. For instance, we have the RAF protocol, which is what beautiful tools like etcd are based on. And well, etcd excels at this, which is one of the reasons why it basically is the backbone of projects like Kubernetes, which takes me to our next topic, the simplicity and all the shiny tools. So a lot of software engineers that currently work with distributed systems, particularly in Go, often come from backgrounds like web, mobile, or product development, anything around product development, where shipping features is the top priority. So I can totally empathize. And then they iterate with continuous integration and development tools till they basically get closer to their ideal state of the product. So the concern is like to ship as soon as possible. So this often means that there is not a long time to think in terms of architecture and planning, and they start coding right away to be able to ship something as soon as possible. In my opinion and in my experience, this is not the most optimal approach for systems engineering and also for infrastructure engineering. If we prioritize writing the code over mindfully planning the interactions, specifically for systems engineering, we end up with a very bloated system or components that are using every other shiny tool, but probably unnecessarily. The more thought we put into the design and interactions, the less amount of tooling we will need in production, which reminds me of this quote by Kelsey Hightower, in which he said, the best way to write reliable and secure applications is to write no code at all. So that is basically to say that if you the code that you don't write won't give you any problems. And this is not just a pun or a joke, it is real, because like the more effective you do your planning, the more effectively you understand your tools, the less code you will require. So this leads me into this advice that might sound too obvious, but in practice, it is not. As developers working for a profitable company, for example, we're pushed to ship as soon and often as possible, as I said. So with these new shiny tools, we are presented with at a very rapid pace. And almost all of them have very brilliant people, very brilliant teams working behind them to make it happen. For different reasons, they often fail to communicate everything that they are actually capable of, while highlighting a very shiny function that is always communicated in a way that is made to sound that it is exactly what we're looking for. And I don't blame them. Unfortunately, in my opinion, this has led us with an ecosystem that looks like this. By the way, this slide is not a mistake. I pasted this image in purpose with this quality and resolution because it is exactly what you find when you go to the website landscape.cncf.io. While every individual tool is made by teams of extraordinary people with loads of experience in their domain, it certainly is overwhelming to try to pick a stack these days, like made up of these tools, particularly if you're just trying to pick something that was supposed to make your life better and quick and solve a very quick problem. And well, I explicitly decided to focus on a cloud native ecosystem because most of these tools are written in Go and a little bit of Bash or a lot of Bash, but let's say with Go. I remember that back in the day when Go was in its infancy, one of the selling points of the language was that the standard library was so complete and powerful that you wouldn't need a lot of external dependencies to write fast and reliable code. It was simplicity at its core. Of course, there's always room for evolution. I'm not saying that you should remain static in your purpose, but I also think that a balance must be kept. Well, speaking of tooling and all of these modern items that we use to build more reliable systems, we have monitoring. And my philosophy for this is having effective metrics and avoiding babysitting. So I often see one of the pitfalls that I often see with monitoring tools are teams that have too many metrics because they think that the more metrics they have, the more insights they will end up having and more data they will have in the end to analyze the performance of their systems. That will probably help them make better decisions for future implementations, future designs. But I often see that this leads to two common scenarios. The first one is that you're not monitoring your system anymore. You're babysitting it, like basically just putting like fences around every single item or every single component. And also this leads to burnout, both on the architectural side, but also on your engineering team side. Creating custom dashboards and really reflecting on them, like this can mean like having a postmortem or like a document discussing this formally or informally, or even creating your own statistics, like mathematical statistics, but on your own, based on your own business requirements, really helps. At work, when we have to work together with the observability team, shout out to my friend Brian Knox, they always beg us to strive for simplicity in the metrics we decide to collect and pay attention to. Less is more, because like this allows a situation in case something goes wrong, having only the most valuable metrics helps the logging system to be more efficient rather than just trying to scrape through all of that amount of metrics. So for monitoring, less is really more. Also, this ends up dramatically affecting your on-call policy for the best. And I can tell you this because this can literally make a difference in how your teams experience being on call. We all know the engineer that gets paid 15 times during their on-call shift, 15 times a day. and that even has to go to family meetings or to anywhere with their backpack, and like be working there, because everything relies heavily on those metrics, or you have false alarms or any type that of indication that that clearly makes your system very bloated, both in the code or in the notifications. And we all know people who maybe work at like very impressive systems and that rarely get paid. So I'm not saying that this is the only thing that makes a difference, but it certainly makes a lot of difference. And it is funny because in the first case, and of the type of engineer that gets paid many times, and most often in the middle of the night. uh, I find it funny and contradictory because these tools were created partially to avoid that very thing of like being awakened by your um, servers or whatever, because they are crashing at 3 a.m. and that you have to restart them, or all those things that people in the olden times have to do. And then with all of this on-call tools and monitoring tools, they end up doing the same. So you have to find a balance in that. And then, well, speaking of balance, it leads me to number 5, is Kubernetes. This cannot be your fault tolerance policy. I'm sorry, but it cannot. And I'll tell you why. Going back to Elixir, for you to understand the importance of not using Kubernetes as your fault tolerance policy, or at least not 100% of it, I wanted to give you a quick comparison of how the Beam, which is the virtual machine that powers Erlang and Elixir, and Kubernetes tackle fault tolerance, among other concepts that either make it possible or interfere with it. And this comparison is not like whether to choose the Beam or Kubernetes. It is more for you to understand at which level of the OSI model is of this tooling works, right? So feel free to substitute Kubernetes with almost any other cloud native tool, and substitute the Beam with Go. Obviously, if you do that, it will have different capabilities, but this chart hopefully will be helpful for you to understand that. So first of all, the fault tolerance. Kubernetes automatically restarts containers that fail, while the Beam restarts parts of the application only. How they supplement each other is that if we have a failure on the application level that makes it or parts of it unresponsive to health checks, Kubernetes will act, saving the whole thing. So you decide whether that's what you want or not. On the other hand, having control of fault tolerance from a language level, like Elixir, makes it easier to make more granular decisions to define a failure policy. The second item is service discovery. Kubernetes does this natively by automatically listing and managing the connections of the existing nodes. You don't have to be like, oh, this is better than this. It's just about different approaches and why you cannot make one tool act as a replacement of the other, because they definitely work at different parts of the layers of the OSI model, for instance. And 3, the live code changes. Both ecosystems support it, but Kubernetes does it with rolling updates, which means that updates happen in small subsets. So this obviously dramatically affects, for better and for worse, the reliability and fault tolerance and all that. And the Beam does it by hot swaps, which was very popular for telecommunication purposes, because as you may or may not know, Erlang was created by Ericsson for telecommunications, with telecommunications in mind. So basically, it all comes down to the layer of the system that we're working on. For this example, I use the Beam and Kubernetes, but as I said, think of any cloud native tool. So, well, we've finally come to the final thoughts that are just a conclusion. Number 1, expect failures, but don't let them cascade. Design with them in mind. Second, Go doesn't provide fault tolerance out of box. Implement it thinking in terms of isolation of components. Design your systems to fail, not provoking them to fail, unless that's what you want for testing purposes, but considering that that could happen, and what are you going to do other than having a babysitting monitoring policy to wake up your engineers at 4 a.m. 3, before choosing more tooling, make sure that the existing one is already fulfilling its full purpose without just adding more stuff. 4, write less code. Take advantage of the standard library of Go. Remember the original purpose of simplicity of the standard library, that you didn't have to add a lot of external components like in other languages. Um, be mindful of your tooling, and the secret sauce is planning, planning, planning before writing a single line of code. 5, monitor effectively, less but more meaningful metrics. 6, all of this, remember, will positively impact your on-call policies, and hopefully your team will thank you. And 7, use Kubernetes wisely. It can be part of your fault tolerance policy, but only after you really understand what layers of the OSI model, for instance, it works at, and where can your Go code take care of it without any additional frameworks, or with additional frameworks, third-party tools, but that really makes sense to what you're trying to achieve. Well, thank you so much for attending my talk. If you have any questions about it, if you want to chat about distributed systems, you can reach me at vlopez@digitalocean.com, Maria Fibonacci on Twitter, and you can find me as Verónica in the Kubernetes Slack. Thank you so much.